Welcome to homework.
Okay, we're told that the mass of a helium atom is equal to 4.0026 AMU, and that its average velocity at 25 degrees C is 1.36 times 10 to the third meters per second. And the question then is, what is the uncertainty, delta x, the uncertainty in position, delta x, of a helium atom if the uncertainty in its velocity is 1%. Okay. Well, recall the how we're going to treat this is that from the uncertainty principle, we know that the uncertainty in position times the uncertainty in momentum is greater than or equal to. So we're just basically going to treat this as equal to for now. Planck's constant over 4 pi, right? Or you could say h bar over 2, same thing, because Planck's constant over pi equals h bar. Okay. And then recall that momentum is simply mass times velocity. And so our sort of operative equation is that delta x is equal to m delta v, right? There's no uncertainty in the mass. So we're saying that delta p is equal to the mass times the uncertainty in velocity, because the uncertainty in momentum is purely related to the uncertainty in velocity and doesn't have anything to do with mass. It's just a constant here, is equal to reduced Planck's constant over 2. Okay. And we know that this velocity is going to be, this uncertainty in velocity is 1% of the velocity that we were given, right? So if it was 1.36 times 10 to the third, then the uncertainty is 1% of that, right? So delta V is going to be this divided by 100, or 1.36 times 10 to the first meters per second, or we can say 13.6 meters per second. So this is the uncertainty in velocity. That's our delta V. Now we need the mass, as we said, but this is an AMU and we need SI units, right? So what's the relationship between AMU and kilograms, right? So recall that this is equivalent to 4.00026 grams per mole. And we don't want per mole, we want per atom, right? So how many atoms are in a mole? Right, so we need to get rid of moles and get per atom on the bottom. So in 1 mole, let me make myself a little space here. Okay, so in 1 mole, there are 6.022 times 10 to the 23 atoms. Okay, that would give us per atom. And then also we need kilograms, not grams. So we're going to say in 1 kilogram, there are 1,000 grams. Right, grams cancels with grams, moles cancel with moles. We're going to get kilograms per atom once we plug this into a calculator, which I will do off to the side here. 4.0026 divided by 6.022 times 10 to the 23rd divided by 1,000, and we will get 6.647 times 10 to the negative 27 kilograms, and that's per atom. So a single atom weighs 6.647 times 10 to the negative 27 kilograms. So now we have the information we need to pull down here. Okay, 1.36 is our delta V. Well, let's bring down the the mass first. We said 6.647 times 10 to the 27. Okay, and then the uncertainty and velocity was 13.6 meters per second. Okay, and we'll rearrange to solve for delta x. We'll just divide by 6.647 and 13.6 on either side of the equation. And let's plug in Planck's constant, Planck's reduced constant while we're at it. Reduced Planck constant. Reduced Planck constant. This would be in your textbook, or you could just Google it, right? And let's take a look at the units as well. So we're told that it's 1.05. Let's say 46 times 10 to the negative 34 joules times seconds. Remember that a joule is a kilogram times a meter squared over a second squared. Right, so if we put this in base SI units, we have 1.0546 times 10 to the negative 34 kilogram meters squared per second. All right, and once we divide these over, note that we'll lose the kilograms, one of the meters, and the seconds. And so we'll have an answer in units of meters, which makes sense for uncertainty and position. So we're all good in terms of units. Just wanted to point that out. Okay, so delta x equals 1.0546 times 10 to the negative 34 kilogram meters squared per second, all over, they're going to have 2 times 6.647 times 10 to the negative 27 kilograms times 13.6 meters per second. Again, kilograms cancels with kilograms, meters per second cancels with one of these meters, and that's seconds, leaving us just with meters, which is good. Okay, now let's plug this into our calculator and see what we get for our final answer. All right. So we get 1.0546 times 10 to the negative 34 divided by 2 divided by 6.647 times 10 to the negative 27 divided by 13.6. And in the end, we get an answer of 5.8333 times 10 to the negative 10th meters. So that's a tenth of this is an angstrom, right? So 5.83 angstrom. We could also say that it's 5.83 times 10 to the negative, times 10 to the 2 picometers, or put this in another useful unit, which would be 0.583 nanometers, so like half a nanometer.